Okay, this is section 3.2, video B. We had been discussing linear regression, extrapolation, and in that same vein, we're going to be discussing what is known as a residual. Okay, if you think about the root word here to this word residual, it is residue. And so if you've ever heard it used in the context of, oh, that surface feels like it has a little bit of residue on it, it usually means that there's something been left on the surface. You can feel something left over. And so if you keep that in mind, leftover, that helps us kind of remember what a residual is, okay? The residual is kind of that leftover or that difference that is between the observed value, and by observed value we mean the point in the scatter plot, the original value of your response variable, and the value that was predicted by the regression line, okay? So there is a formula for calculating the residual, and then I'll show you kind of graphically here in this picture off to the right what visually a residual would look like. But the formula is you take the observed y value minus the predicted y value. And what I like to remember this as is I like to think AP, since this is an AP class, and I like to remember it like this. I take the actual y value and I subtract from that the predicted y value, okay? Keeping in mind that the actual y value would be the point that's in the scatter plot, okay? That's the point in the scatter plot, and then the y hat, or predicted y value, is the point on the regression line, okay? So you can see here pictured, we've got some points in our scatter plot. You can see this blue regression line running through, and that vertical distance from the actual point to the regression line, that is what is known as the residual, okay? That's the residual. It's that vertical deviation from the line. And so we're saying, okay, what's the difference between the observed value in the scatter plot and the value that was predicted, okay? So your residuals are positive if these vertical distances are above your line, and your residuals are negative if these vertical distances are below the line. And you want to keep in mind that it's always actual minus predicted, okay? So if you're getting a positive residual value, that means that your predictions have actually under-predicted what actually occurred. If you're getting a negative residual value, then your predictions are over-predicting what actually happened, okay? Here's how to calculate a residual, okay? There's 3 steps here. It says you're going to calculate the predicted y hat value by plugging the given x value into your least squares regression equation. Then you're going to determine the observed value of y. That should be given to you in the scatter plot. And then you would simply subtract, again, just think AP. Okay, you're going to subtract actual minus predicted. Okay, here is a template for how to interpret residuals, and we'll take a look at doing this together here. But the template is you say the actual, and whatever your y variable is in that problem, for the specific value of x, and give that context, whatever its variable is, okay, and then you say the residual, and then you say that that it's that much of the y variable is either less than or greater than, and it depends on whether your residual is positive or negative than predicted, okay? So if you're doing actual minus predicted, if the actual is, the predicted is being subtracted from the actual, okay, then that's why we're saying it's either greater than or it's less than what was predicted, okay? So let's look at this example, okay? Here we have a student weighing 170 pounds. So our x variable is the body weight of a person. The y variable here is their backpack weight, okay? And we want to say if a student weighs 170 pounds and their backpack weighs 35 pounds, what is the value of the residual? Okay, so we're talking about this person right here, represented by that point in the scatter plot. The x variable is 170, the y variable is 35. So this is a 170 pound person carrying a 35 pound backpack. Okay. Now remember our steps here. Okay. If we want to calculate the residual, we're looking for what this vertical deviation is here. Okay. Step 1 is we need to calculate what was the predicted backpack weight of a person who weighed 170. Okay. So we are taking the given x value, and we are going to plug that given x value into our regression equation. By the way, the equation is right here on the graph in that little box, okay? So we're going to plug 170 in for the x, and that gives us a predicted backpack weight of 31.73, okay? So that means the y value of this point is 31.736 pounds, and we're interested in what the difference is in between those two y values, okay? So again, we want to think, okay, residual is actual minus predicted. So the actual weight of the backpack is the 35 that was in the scatter plot. The predicted is the 31.736. That means the residual is 32.64 pounds. Okay. Now I'm going to fill in my explanation of that. I'll just fill it in right in here in the template. Okay. So what we would say is the actual pack weight. Okay. That's what our y variable is. Our actual pack weight for a 170 pound person is, okay, and then this is where I'm going to fill in the value of the residual, is 3.264. My x variable is pounds. Pounds, I'm choosing greater than predicted. Okay, so if your residual is positive, then the actual is that much greater than the predicted. If the residual is negative, then that means the actual is that much less than what was predicted. Okay, it's in the order AP, actual minus predicted. Okay, now it says in part B, if a student weighs 105 pounds and their backpack weighs 24 pounds, what is the value of the residual? Okay, so they're saying that this is the actual point. Okay, 105 and 24. Assume they're talking about this person right here. Okay, so my first step is to figure out, well, what would have been the predicted pack weight for this person? So I'm going to go ahead and plug in the x value, 105 pounds. This is going to be what would have been predicted for their backpack weight, 25.834 pounds. Okay, now my formula is residual equals actual minus predicted. Okay, so to get the residual, I'm going to take the actual y value, that's the actual backpack weight, 24 pounds, subtract from that the predicted backpack weight, and that gives me a negative residual of negative 1.834. And you can see in the picture, see how that vertical distance was underneath? Okay, so you got to think back and say, I did the actual first. So when you go to write your description from the template here, you always start out by saying the actual, okay, because that's where you started here in the formula. So we're going to say the actual pack weight for a 105-pound person is 1.834 less than predicted. Okay, you don't put the negative in here, you're addressing the negative when you say less than there. But you always start out with the word actual because that's how the formula is. It's actual minus predicted. Okay. Now there is such a thing on your calculator called a residual plot, and we will learn tomorrow how to make residual plots on our calculator. For today, I just want to show you what a residual plot is and how to read and interpret one. Okay, so a residual plot is essentially a scatter plot of all your residual values plotted against the explanatory variable. Okay, and what it helps us do is residual plots help us determine or assess how well a regression line fits the data set. Okay, how good is that regression line in terms of answering some predictions here? Okay, so you can see pictured on the left, this would be just original scatter plot. Notice that our X variable, our explanatory variable, has something to do with the amount of calories burned from a non-exercise activity. And then it looks like the Y variable is the fat gain in kilograms. Take note that over here on the right side, now our Y variables are what are called the residual values, but the X variable is the same. Okay, and that's what we mean here when we say a residual plot is the residuals are plotted against the explanatory value. So those are still the X's, but then paired up with each X value, you plot as its Y value what the residual is for that. Okay, so in other words, if I flip back to this graph here, this was the 105-pound person. If we were making a residual plot, okay, I would need to plot the point 105, comma, and then I would pair up with the 105 the value of the residual for that, which was this negative 1.834. And I would plot that point. It would maybe be, if this was 100 and this is 120, I would maybe say that, roughly right about there would be where that point would fall. Okay. All right. So how do we interpret a residual plot? Like we can see here that you'll notice that on the residual plot, 0 is this, like the value of a residual of 0 runs right along what looks like that x-axis. Now keep in mind what a residual of 0 means. If you get a residual of 0, that means your actual point in your scatter plot was exactly on your regression line. And so there was no, we over-predicted this or we under-predicted this. The actual was greater than or less than what was predicted. It was spot on, and so you would get a residual of 0. Okay, it doesn't happen a lot, but any of the points in your residual plot that are above this value of 0, okay, those are residuals that are positive, and then anything underneath those had residual values that were negative. Okay, so when you're looking at a residual plot, this is what we use them for. We use residual plots as a tool to evaluate the form of the model, okay, and decide whether it's appropriate or not. Now, in this class, we will only be running linear regressions, okay? So in essence, a residual plot will tell us if a linear regression is a good fit for that set of data, okay? Now, here's what you would be looking for, okay? You would want to make sure that your residual plot does not have any distinct pattern to it, okay? It should really just look like kind of the night sky, like these random points. There's a random amount above the residual line of 0, and there's a random amount below. And so we got equal amounts that have positive and negative residuals. Okay, if you notice a residual plot, and I think we might even have one pictured underneath here. Okay, well, let me just sketch one here. If you notice that you have a residual plot, and that residual plot feels like, you're seeing some type of distinct pattern to the residual plot, that's an indication that a linear model was not appropriate at all. Okay, it should feel very random. That's why it says kind of like a night sky. If you see just random scatter, some above, some below, that is telling you that running a linear regression for your original data set was an excellent fit. Okay, so what we're going to do here is it says to the left is the linear regression line, and to the right is a residual plot. Okay, so here's the original set of data. We've got the line of best fit going right through there. Okay, this is our residual plot, so it has the x values graphed against their residual values. Okay, take note that right here is a residual value of y equals 0. I would look for some equal amounts above and below. I don't really want to see any type of pattern here at all. So we want to determine whether the linear regression is a good model for this original scatter plot that was over here. Okay, I'm going to say yes, a linear model is appropriate. And here's my reason. There is no evident pattern in the residual plot. This is a common statement that is made when you're looking at a residual plot. You shouldn't just say, oh yeah, a linear model is appropriate because I looked at the residual plot and I think it's appropriate. You need to say, what is it that you noticed in the residual plot that is leading you to the conclusion that a linear model is in fact appropriate? And you would say, well, I'm seeing no evident pattern there. Okay, now, this might seem kind of obvious, and they're not always this obvious. Look at this next example. Here's the original scatter plot, which we can probably say, we definitely see a curve here. So that would be an indication that we might be able to tell that a linear regression is not the best regression to be running to fit this data. Okay, but when we make a residual plot, again, we're saying that our residuals are our y values. Okay, you can clearly see that we have got a distinct pattern in the residuals. So I'm going to say no, a linear model is not appropriate. And I'm going to say there is an evident pattern in the residual plot. Okay, now here's often what happens. If your original data set, in fact, is a curve, okay, but we know that you can have a parabola, but if you only zoom in on a small part of the parabola, okay, like let's say our scatter plot just had a few points like that, it would be much more difficult for us to decipher with the naked eye that there's a curve happening here. It might feel more linear, okay, but the calculator, when it runs its residual plot, it will be able to detect that pattern and that curve, and it'll come out in the residual plot that you might not have been able to tell by just looking at the original scatter plot there, okay? So it says in example 6, it wants us to determine whether a linear regression is the best model for this original scatter plot. And you can see here that I've answered these for you. And by the way, we don't have the original scatter plots to look at. These are residual graphs. Okay, so, and we will discuss tomorrow how to make a residual plot on the calculator. But this is a great residual plot. There's lots of random scatter above and below our line of where it equals 0 here. So we would definitely say that a linear model is appropriate for the reason that there's no evident pattern. Okay, this one over here, it definitely feels like there's a pattern. These are kind of going in increasing order from left to right. They're going up. Okay, so for that reason, remember, this is the residual plot we're looking at. We're not going to say that a linear model is appropriate because it feels like there is some type of pattern happening here in this residual plot. Okay, let's see if we can pull together everything we've discussed so far in this section with this example here. Okay, and this is going to give us an opportunity to kind of run a regression on our calculator. So I want to give you just a second. I would like for you, this is talking about a student who ran a 40-yard dash. They did a long jump immediately after they ran this 40-yard dash. They did a long jump. And it says here that the 40-yard sprint times, that's these values at the top in seconds, and then the long jump distances are below here in meters, okay? So we're going to have our sprint times be x, our long jump distances are y. I would like for you to type the sprint times into L1 and the long jump distances into L2, if you would please. Okay, you can pause this video and go ahead and input that data. Okay. All right, now for part A, it's asking us to run a regression. Find the least squares regression line for the sprint times in seconds and the predicted long jump time in inches here. Okay. Now, when we do this, and I have already, oops, I'm going to have to log back into this here. Sorry about that. Okay, I've already put the data into my calculator, into L1 and into L2. Okay, so I'm going to walk you through this. By the way, on the very next page here of your notes, it has all of these key presses and some screenshot examples. But you would press the black stat button on the calculator. This is going to register for me here. Maybe it will, maybe it won't here. Okay, you're going to press that black stat key. And then you're going to bump over to the edit menu. Okay, let's see here. For some reason it's not. Okay, my apologies earlier about that with the calculator here. What you would do, I'm assuming you guys are aware of this, you're going to press that stat button. You're going to press 1 for edit, and this is where you would input all the values, which I have already done at this point. Okay, now to run the regression for part A, okay, if you press the black stat button and bump to the right to the calculate menu, I think we are used to in Algebra 2 choosing option 4 for linear regression, but if you recall in statistics, we use the b value as our slope and the a value is the y-intercept. So if you could scroll down, you should see an option 8. Okay, option 8 on your calculator. It's also called linear regression, but do you see how the variables are flipped? This is more how the formula would look on the AP test, a plus bx. So I want you to choose option 8, okay? And then we're going to come down here and we're going to, I always like to put the variable y1 across from store regression equation. So if you move the cursor there, press the black vars button, press to the right for y vars, and then press 1 for function here, and then 1 for y1, and then you can come on down here and press calculate and enter, and it should run a linear regression, and you would just round the a value to 2 places and the b value to 2 places. Now I should mention, so we would write down on our paper here, let me go ahead and do that. We would write down that our regression equation, we could do this a couple of different ways, but it's very important that you put the hat symbol over top of your y variable. Okay, so we could write it like this. If I'm using x's and y's, I need to define what these represent. So I'm going to say this is the predicted long jump distance, okay, and that's in inches, and then my x is the sprint time. Okay, of course, and that's in seconds. Of course, you also could use the words right in the equation, and that would be fine as well. Okay, what I just want to mention here is back on the calculator, you'll notice I didn't get the correlation coefficient in R value when I ran this. That's because I didn't turn on my diagnostics. This is typically a one-time thing. You should only have to do it once. You're going to go to second and then 0. You're actually selecting the catalog when you do that. You can scroll down to the D's if you like, or I hit alpha D, and that takes me down to the D's in the catalog. This is just a little bit delayed here. Okay, let me try this again here, see if it'll register. Alpha D. What you're looking for is you're looking for the command diagnostic on. So you would want to scroll down until you see the command diagnostic on. Whoops. Okay. here. I'm having some tech issues here. Sorry about this. Okay, so I'm going to scroll down to diagnostic on. Press enter once I get to it. This is just a little bit delayed here. Okay, there we are. And then now if I were to run the regression, it would also pull up that R value, which would tell me about the strength of the correlation. Okay, I just wanted to mention that. Once it's turned on, it shouldn't be a big deal. Okay, all right, let's go back to the notes here. It wants us to interpret the slope of this line in context, and that's what we did in the previous video. Okay, so recall here, the slope on this problem is the negative 45.74. So we could say it's always for every 1 unit increase in x, but you got to use context. So it's for every 1 second increase in sprint time, very important that you've got the word predicted here. The predicted, then our y variable is long jump distance, now remember, the slope was negative, so it is decreasing by 45.74 inches. Okay, to interpret the y-intercept, that's this 414 number. We could say when the sprint time is 0, or if you just wanted to say when you do not sprint before you long jump, that would be the same thing. Again, super important that you have the word predicted here. The predicted long jump distance is 414.79 inches. Okay, these words predicted are crucial in these interpretations. Okay, part D. Find the long jump distance prediction based on your linear model for the person whose sprint time was 6.73. Okay, so we are looking for the prediction. That means I'm going to use my regression equation. The person who sprinted, remember the sprint time is your x variable, who sprinted 6.73 seconds, they would have been predicted to long jump 106.96 inches. Okay, so I'm going to just write out that interpretation. When someone sprints 6.73 seconds, the predicted long jump distance is 106.96 inches. Okay, now this is what we talked about today. It says find and then interpret the residual for a person who sprinted in 6.73 seconds. Okay, so let's remember this. Our residual formula is AP, actual minus predicted. Okay, now what you're subtracting here are always the y values, the actual y value for a person who sprinted 6.73 minus the predicted. Okay, well, the actual is the point in the scatter plot. So let's look back up top here and say the person who sprinted 6.73, they actually long jumped 78 inches. Okay, so I'm going to be using 78 for the actual. The predicted is that answer from part D, the 106.96, for a difference of negative 28.96. So I'm going to say for my interpretation, always start out with actual because that's what we start out with when we do our subtraction. The actual long jump distance for a person, let's see here, sprinting 6.73 seconds is 28.96 inches less than predicted. Okay, that much less than predicted. All right, part F here. We're almost through this. Okay, part F. Would this regression line be more useful for predicting the long jump time of a student that runs the 40-yard dash in 6 seconds or a person who runs the 40-yard dash in 9 seconds? Why? Okay, let's go back and look at what our range of x values were, because keep in mind, these are the x values, these are the times. Let me go back and look at our data set. Look at these times. Okay, it's asking 6 or 9. It feels like most of these span from the 5-second range. The highest time I see is this 7.25. There were no sprint times even really close to 9 seconds, but 6 seconds is within this range of intervals. I definitely don't want to be doing any extrapolation. So I'm going to say that the 6-second time would be a better prediction. And then I'm going to comment why the 9-second wouldn't be as good. 9 seconds is outside the interval of explanatory values. Those are my x values. This would result in extrapolation. Okay, extrapolation is what we called it. Okay, and then our very last one here, and you got to really read this carefully. I've seen lots of problems similar to this. You might have something like this in a McFrappy packet coming up, or in the homework. It says, suppose we use this regression line to estimate the long jump distance of a 13th runner who ran the 40-yard dash in 6 seconds. Okay, the residual, look at what they're giving you here. They're giving you the residual for this person was -6 inches. Find the actual long jump distance for this individual. Okay, so here's where they're saying, look, we're going to add another person to this group. They took 6 seconds. We don't know what their actual long jump distance is. We only know the residual. If you always go back to the formula and you just kind of write the formula down, it really helps you see what you need to do to get the actual. Because there's really 3 variables here. Residual, actual long jump distance for the 6-second sprinter, and the predicted long jump distance for the 6-second runner. Well, we know the residual is -6, so I'm plugging that in on the left side. The actual is what we're trying to solve for. And I should be able to figure out the predicted by using the equation up above, okay? The regression equation with 6 plugged in for x is going to give me a predicted long jump distance of 140.35 inches. Okay, so then I'm just going to use algebra and I'm going to move this -140.35 over to the other side so that this is going to be solved for actual long jump distance would end up being 134.35 inches. Okay, this is the page where if you needed any refreshers at all,